In this video, we will talk about how to graph an elliptic paraboloid. So this will be our first example of what's called a quadric surface. Okay, so I want to begin by writing in a table here what a quadric surface equation looks like. Okay, so when we talk about two-dimensional objects, we've talked about conic sections, and in general, the equation of a conic section looks like the following: ax squared plus by squared plus cxy plus dx plus ey equals f. So a conic equation looks like that. It has degree 2, that's the highest power of the variables, and there can be two variables like this, an x and a y. So when we go one dimension up, 3 dimensions, we get to quadric surfaces. And the equation of a quadric surface looks like ax squared plus by squared plus cz squared. And then you could have all the mixed terms, so with two different variables together. So dxy plus exz plus fyz, so all of those terms. And then you could have terms that just have the individual variables by themselves, like gx plus hy plus iz. And this whole thing might be equal to some constant on the other side, so equal to some constant j. Okay, so in both conic equations and quadric surfaces, we are looking at degree 2 equations, or I'll call these quadratics, because they have degree 2. And that's one of the reasons why these are called quadric surfaces. It just is talking about the fact that it's degree 2, or quadratic in a sense. So one quick thing that I want to comment on about quadric surfaces and about what the terms tell us about the graph is these terms that just have one of the variables on its own, so like x or y or z, they shift the graph. So instead of it being centered at the origin, that's what the gx, hy, iz would do. They would shift it away from the origin. And then these mixed variable terms that have two different variables together, they rotate the graph. So in the basic types of quadric surfaces that we are going to look at, we're not going to do any examples of things that get rotated. But I just wanted to comment on this, because in general, that's what these mixed terms would do. They would rotate the graph. All right, so in the last video, we talked about how to graph things where one variable was missing, or we call that free. And when that happened, we get a cylinder. We get a cylinder. In this video, we'll talk about, well, what if no variable is missing? If no variable is missing, it's useful to look at cross sections of the graph. Cross sections. Okay, so for example, doing things like setting x equal to 0. So x equal to 0 is looking at the yz plane and thinking about, well, when is our graph going to meet the yz plane? Or when does it intersect the yz plane? Okay, the other cross-sections, basic cross-sections we might look at are y equals 0. And that's talking about the xz plane, and when our graph meets the xz plane. We do z equals 0, and that's the xy plane, and we'd be asking ourselves, when does our graph meet the xy plane? Okay, and then after that, if necessary, we could look at other examples like z equals +1 or -1, and we keep going like this, so etc., until we know what the graph looks like. So it's not always set in stone that we'll look at z equals +or -1. Sometimes we may have to do a different variable like x equals +or -1 or y equals +or -1, and we might continue like do +or -2 or +or-3. It just kind of depends on the problem. All right, so let's start looking at an example. So, an example, let's graph, let's zoom it out a little bit. Let's graph x squared over 4 plus y squared over 9. Let me write that better actually. Y squared over 9 equals negative z. Alright, so I'm going to begin by looking at these cross sections. So let's look at x equals 0 first. Let's set x equals 0. And if we do that, we get y squared over 9 equals negative z. And I could isolate the z by moving the negative over and get z equals negative y squared over 9. So I'm going to first draw that in the yz plane. So in the yz plane, and then I'll translate it to xyz space. So in the yz plane, this is the graph of a parabola, and it's downward facing because of this negative sign. And having this 9 on the denominator is going to sort of make the parabola a little bit more horizontal than it would typically look like. So a little bit more stretched out horizontally. Downward facing, a little bit stretched out horizontally because of that 9 in the denominator. Alright, and now let's draw it in 3D space. So I'll have a z-axis, x, z, and a y. And I'll draw the negative directions. So negative z, negative x, and negative y. So when I draw it here, I need to draw it subject to the restriction that x is equal to 0. And that means it's on the yz plane. So yz plane, it would just look something like this. So something like this, but I really want to try to visualize this in 3 dimensions. This is on the yz plane. Alright, so that's one of my cross sections right there. Let's now take some more. So let's do y equals 0 next. So if we plug in y equals 0 into this equation, we get x squared over 4 equals negative z. And isolating z, we get z equals negative x squared over 4. And now let's graph this. Let's graph this first. Let me zoom it out a little bit. Let's graph this first in the xz plane. So I'll draw just 2 axes, an x and a z. And let's graph this in the xz plane. Okay, so when I do this, it's going to be another downward facing parabola because of this negative sign. And the 4 being on the denominator is going to stretch it out a little bit horizontally. Okay, so it again is going to be stretched out horizontally, not quite as much as the last one. Okay. And I'm deliberately going to draw it in a different color in the other direction, in the negative x direction. And we'll see why once I draw it in 3D space, why I'm doing this. Okay, so let me begin to draw this in 3D space. Let me zoom it out a little bit more. So now in 3D space, I need a z-axis, an x-axis, and a y-axis. Let's draw the negative directions. So the negative directions. Okay, so first I'm going to draw the green part of my parabola. So that's in the positive x direction in xyz space. So the positive x direction is this way. That's the positive x direction. Okay, so I need to draw this in the xz plane because that's what I get when I look at the restriction y equals 0. That puts me in the xz plane. Alright, so that would begin at the origin, and it would curve out this way. So it would come forward because forward is the positive x direction. Okay, now let's draw the orange part of the graph. So the orange part of the graph is extending in the negative x direction. So that needs to be going this way. It needs to be going this way. So again, I have to draw it in the xz plane. So that would look something like this. Something like this. So that's continuing my parabola, but in the xz plane. So this cross section is a little bit trickier, at least in my opinion, to visualize. So I'm going to try to draw the xz plane, or a parallelogram, to sort of represent the xz plane. So if I draw in that parallelogram, I would have something sort of going up parallel to the z-axis and down parallel to the z-axis. And then parallel to the x-axis from here. Same thing from the bottom, parallel to the x-axis. And then at these endpoints now I draw a vertical line down parallel to the z. And imagine that that's my xz plane. And it extends infinitely. So it extends infinitely this way and down and forward and up and forward and down. Okay, but so this green and orange parabola that I've drawn is on that xz plane. Alrighty, so let's look at some more cross sections. So I just have 2 cross sections so far. Let's look at some more. So next, let's set z equal to 0. So if we do z equal to 0, we get x squared over 4 plus, y squared over 9 equals 0. And thinking about this, there's only one choice of x and y that satisfies this equation, because the squareds make everything non-negative. So the only way for it to equal 0 is if x equals 0 and y equals 0. And that means that our graph for this cross-section is actually just one point. It's one point. It's the point where x is 0, y is 0, and z is 0, because that was our restriction we were looking at. Okay, so that's actually going to be the origin. That's the origin right here in the graph. So we actually already had that kind of drawn in. Let's do another cross-section now. Let's start to do different values of z. So if I do this, if I pick z equals 1, we get x squared over 4 plus y squared over 9 equals -1. So because these squared terms are non-negative, there's no way when we plug in values it's going to equal -1. The smallest the left-hand side could have gotten was 0. So this equation is going to have no solution. And what that means graphically is that the graph just doesn't intersect the plane z equals 1. Alright. In fact, we might be able to see at this point that no matter what positive value of z we take, like if we were to take z equals 2 or z equals 10, it's going to make the right-hand side negative, and we're not going to have a solution. So let's start to take cross-sections where z is negative. Alright, so let's look at z equals -1. So if we do that, we get x squared over 4 plus y squared over 9 equals, we'll get -1 on the right, which is +1. Okay, and this equation is an ellipse. This is an ellipse. Okay, so I'm going to start to draw this as a 2-dimensional graph in the x-y plane first. Okay. And it turns out that if I find the intercepts of this, the x-intercepts are 2, 2, and -2. And the y-intercepts are 3 and -3. So it's stretched more vertically than it is horizontally. So my graph is stretched more vertically than it is horizontally. Okay, so it looks something like this. My graph is not perfectly to scale. I made it look more like a circle than an ellipse. But I have this nonetheless. In fact, maybe let me just draw that a little bit better. Let's not spread out these x tick marks quite so much. Let me just begin by drawing it a little bit more vertically. So I'll make it a little bit more narrow. And then I'll put in the tick mark. So this one's at 2. This one's at -2. Okay, so before I draw this in 3D space, let me also draw one more of these cross sections when z is a negative. So let's pick -2. And that'll give me x squared over 4 plus y squared over 9 equals -2, which is +2. And that's another ellipse. So this one is another ellipse. And this one's a little bit bigger. So I'm going to draw it in first, and on the same graph that I've drawn above. This one's a little bit bigger. A little bit bigger. It's still stretched more vertically than it is horizontally. It's a little bit bigger. The x-intercept of this one on the positive side ends up being 2√2. And at the top it ends up being 3√2. Okay, so those are those cross sections, but when I just draw them on the xy plane, now let's draw them in 3D space. Okay, so let's make our 3 axes, z, x, and y, and let me draw the negative direction, so -z, -x, and -y, and let's start to draw these. So for this first ellipse, it's subject to the restriction that z equals -1. So that means when we're at the intercepts, so when we're at this y-intercept, which is 3, and the x-intercept, which is 2, we have to go a distance 1 down from those x-intercepts. So let me also draw the negative intercepts, the negative y-intercept, and the intercept and the negative x direction. From each of those, I have to go a distance down of 1. So distance down 1 from this one, down 1 from this one, down 1 from this one, and down 1 from that one. And now I connect those points to make my ellipse. So I connect those points to make the ellipse. That's looking something like this. It looks a little bit warped, and that's just because I'm drawing a 3D looking graph. Okay, now let's draw this next one. So for the next one, the intercepts are all a little bit further. So it's a little bit further here, a little bit further there, a little bit further here, a little bit further in that negative x direction. And from these points, I'm going to go down a distance of 2. So I'm going to go down a distance of 2 here, so twice as far. A distance down 2 here, and down 2 here, and down 2 from there. And now I connect these points. So I connect these points, and maybe let me even draw the back as being a dashed line. And I start to get that ellipse. And that ellipse needs to be lower than that first ellipse that I drew. Alright, so now I want to take all of this information that I've gotten from the cross sections and put it together into a graph. Alright, so now let's graph x squared over 4 plus y squared over 9 equals -z. Okay, so I'm going to draw my axes. So z-axis, x-axis, y-axis, and then negative directions. So negative directions. Okay, so for this particular example, one of the types of cross sections that really give me very detailed information were these last few. What was happening is, as the z value gets lower and lower and lower, the cross sections look like larger and larger ellipses as I go further and further down. Okay, so I want to keep that in mind when I try to draw my graph. So I'm going to begin by drawing one of those first parabola cross sections we had. So we had this sort of parabolic cross section. This parabolic cross section. And that cross section was in the YZ plane. And now I'm going to draw in those few ellipses that I had drawn. Okay, so I'll draw in one of these ellipses. So one of these ellipses was at z equals -1. So I'll draw the front part of the ellipse. The back part of the ellipse we won't be able to see, so I'll draw it with a dash line. So dash line. Okay, let's draw the other ellipse. So the other ellipse is going to be lower, so I'll pick a lower starting point here. I'll draw the front part of the ellipse. The back part we won't be able to see, so I'll draw that with a dash line. So draw that with a dash line. And what we're starting to see is this looks like kind of a parabolic bowl shape, hopefully. We're starting to see that. And if I include our very last cross section, that was the parabola that was on the XZ plane. Remember, we had drawn this green sort of arc for when it extended this way. So that green part of the parabola is extending forward. And then for the part of the parabola that was extending back, we drew that in orange. So that part we won't be able to see in the graph. I'm going to draw with a dash line. So the back part is extending downwards like that. And we're getting this parabolic bowl shape. Okay, and this is called an elliptic paraboloid. Okay, so in general, the equation of one of these looks like z equals ax squared plus by squared. Or we could switch the roles of the z and the x and the y, and we could have something like x equals ay squared plus bz squared. Or we could have a y by itself and get y equals ax squared plus bz squared. There's one important thing that we need about a and b is a and b must have the same sign. They have to have the same sign as they did here for this to be the general equation of an elliptic paraboloid. If A and B had different signs, it turns out it's not an elliptic paraboloid. It turns out it's a different shape. And the reason this is called an elliptic paraboloid is, well, these sort of horizontal cross-sections were ellipses, and it's called a paraboloid because the other cross-sections were parabolas. Okay, so the general equation of an elliptic parabola is going to look something like this. In terms of our goals for this section, we have now described how we graph an elliptic paraboloid using cross-sections. In the next video, we're going to apply that technique of using cross-sections to graph a hyperboloid of two sheets.